Hi, everyone. My name is Liam Lee, and I'm a distinguished technologist at HPE. And today I'm going to be presenting on various ways of going beyond GPT-4, and in particular, how to harness the power of LLMs in industry. Unless you've been under a rock, I think we've all seen language models really take over a lot of the zeitgeist in machine learning. And these language models have been trained on a massive amount of text at humongous scale and have been able to unlock a lot of value in various different downstream problems. And underlying these models is a transformer architecture that now have been scaled up to billions of parameters. And at this scale, we've seen really impressive human-like performance start to emerge. So what is happening when we train these large language models, I think is really important to just take a look behind the scenes and understand the mechanics. So we can try to reason about how these models work. So the language models that we are all familiar with, like ChatGPT and GPT-4, are all trained in what's called an autoregressive way. So the language models are trained to take a sequence of text and to basically learn the probabilities of various tokens or the next word given a particular sequence, right? So if we have a sequence that says this 23-year-old white female is present with allergies, and in the past she's tried Claritin, and if we pass that text through a language model, the language model has hopefully learned a good probability distribution for what the next word should be, right? So maybe the probability distribution would place a lot of weight on other types of antihistamines that the patient could also have tried, right? So that's really what these language models are being trained to do. They're being trained to predict the next token, and effectively that turns into learning a distribution over sequences of text. So they're what's called probabilistic language models. And from this very simple modeling problem, just predicting what the next word should be, a language model is able to be used to solve a wide variety of different tasks. So from the latest GPT-4 paper, you can see the performance of GPT-4 in many different tasks that we traditionally use to measure human intelligence, right? So your AP tests here, there's LSAT, there's also kind of medical examinations that are all represented as different bars in this chart. And you can see GPT-4 is able to achieve very high performance on many of the tasks here, and oftentimes exceeding the average human performance. So what does this mean for you, and how can these powerful language models be used in industry verticals? And there are few levels of customization of these language models, and few different ways that you can apply them, and they kind of go in increasing complexity, right? So at the very base level is prompting, where you kind of use the models directly without modifying them. And the next level is fine-tuning, where you're introducing your own data to the language model and modifying it so that it's more customized to your domain-specific data. And then the top level is kind of really restricted to companies that have access to a lot of compute. But at the pre-training stage, this is where you can basically train domain-specific models from scratch. So I won't be talking too much about the pre-training portion of how to customize LLMs for your own use cases. I'll focus on prompting and fine-tuning, because that's where I think a lot of the value can already be extracted. So in the rest of this talk, I'm going to walk you through the two primary approaches of applying LLMs, and first cover the various ways of applying prompting to a custom problem, and then different ways of applying fine-tuning to a custom problem. And then finally, I'm going to tie both of those together into an information retrieval type application. And hopefully by the end, we'll see various ways of how different ways of going beyond just consuming APIs from OpenAI can really help you extract more value from your domain-specific problem. So how is prompting used for language models? And to sort of help us understand, I'm going to be focusing on a particular case study of applying LLMs via prompting for radiology. And the task that we have here is we want to be able to, say, given a passage and a question, determine whether the question can be answered from the passage, right? So that's what that entailment means. So if the question can be answered from the information in the passage, then we should label this example as entailment, or entails the passage entails the question. So how can prompting be used for a task like this? At the very basic level, the first kind of approach to prompting is what's called zero-shot vanilla. I'll just call it zero-shot vanilla prompting. And you can give the language model a prompt that describes the task. So in this case, we're telling the language model, hey, you're a radiologist, and your task is to determine whether the passage entails the question or not, right? So we've described the task, and then we provide the data that we want the language model to classify, right? So so the first part of the system prompt, intuitively, this is trying to basically condition the language model so that it's in a region of a distribution, of a probability distribution that's suitable for radiology, right? So that's what you're really trying to do with the system prompts. So if we give this prompt to the language model, hopefully it will return with the right answer, which is there is entailment. So a slightly more advanced approach is what's called few-shot vanilla. So in the previous example, we didn't give the language model any examples of what we wanted it to do. So we can modify it and insert some examples of passages and the answer of entailment or no entailment, so as demonstrations, so the model can learn from this in context. So this is what's called in context learning. And hopefully, given those examples, it's able to do a better job of providing the right answer for the input that you actually care about. Another approach that's very common is called chain of thought reasoning. And the main difference is you want the language model to explain how it arrives at the answer. So so the reasoning, so in its generation of the answer, the language model will hopefully describe how it determines that, in this case, the lungs are clear can be used to answer the question, is there any fluid seen in the lungs? There's also a few-shot version of this where you can provide examples of reasoning and answer to the language model so that it can hopefully learn from the demonstrations again. So how do these prompting approaches work on a radiology task, on the radiology task that we have in mind? So here I'm comparing ChatGPT and GPT-4 using both zero-shot vanilla and zero-shot chain of thought reasoning. So here, no demonstrations, but in the chain of thought reasoning case, we ask the language model to explain how it arrived at the answer. And the results are kind of unsurprising, right? GPT-4 obviously does better than ChatGPT. And also asking the model to explain its reasoning does better than just asking it to give the answer. Next, we kind of look at the performance of introducing the few-shot variants of both vanilla prompting and chain of thought prompting. And here, the results are kind of counterintuitive, right? So we do see the thing that we expect, where introducing more examples improves the performance. But now the relationship between vanilla prompting and chain of thought is reversed, right? So when we introduce more examples as part of the prompt, chain of thought reasoning actually does worse than few-shot vanilla prompting. And this really indicates a gap in the knowledge of the underlying language model, right? And this can be explained by other observations that kind of observe similar things. But basically the takeaway is that if the language model is not really customized or fine-tuned to a particular domain, we might see this sort of behavior where including more examples doesn't actually help the model learn from those examples and give a better example at the end. So this really gets at limits of in-context reasoning, and we've seen this happen in other domains too. So, in a retrieval type task, as the number of documents, or as the position of the document with the answer is towards the middle, we see the language model is actually has a harder time extracting the information out. So there's kind of a limit to what you can do with in-context learning. Another limit to just consuming the models directly out of the box is they're not very good at learning long tails of knowledge, right? So here it's showing the performance of various size models as a function of how many relevant pre-training documents the model has seen, right? So as you'd expect, the more times a model has seen relevant pre-training documents, then the better it would do on a question answering type task. But for anything that really doesn't show up much in the training data, the language model, even the largest language models, do quite poorly, right? So this is another indication that there's definitely room for improvement if we're able to inject more of our own data into the language model. So this leads us to the next way of applying language models, which is via fine tuning. And if we go back to the radiology case study, fine tuning can be applied in a very straightforward manner. We basically give the examples that we have with the corresponding labels as training data to the language model and ask the language model to predict the next word, right? So in this case, when we get a new example in, the fine-tuned language model can just see the passage, the question, the label, and then it will basically be in charge of predicting the next word of whether entailment or no entailment. And if we apply fine-tuning to the task, we actually see better performance in certain cases, right? So here, this chart is basically showing the performance of the fine-tuned model relative to different prompting approaches, which are the dashed lines, as the number of samples of training data point increases. And intuitively, it makes sense that the performance would increase the more training data points that we have for fine-tuning. And you can see if the data set for fine-tuning is large enough, we can actually outperform 10-shot GPT-4. So there are definitely situations in which fine-tuning makes sense and can help with a lot of the issues that you might encounter when using prompting directly. So to summarize, when are certain situations you might want to consider prompting versus fine-tuning? I think first there's an obvious takeaway that few-shot prompting definitely establishes a very strong baseline. So you can see in our example, ChatGPT and GPT-4 both do pretty well. And the benefits of fine-tuning really depend on a few different dimensions. So one, how unique is your data, right? So this really goes back to the long tail of knowledge. So if your data is very unique, probably doesn't have a lot of representation in the pre-training text corpora, and you might want to consider fine-tuning. Another one is the complexity of the task, right? So if it's a task where you really require the language model to perform advanced reasoning, then you probably need to inject that type of reasoning into the language model so it can successfully accomplish that. Third consideration is the availability of data. So there is definitely some threshold at which fine-tuning may not be as good or may not outperform prompting. So usually I'd say you need at least a few hundred data points, and the more you have, the better. In our case with radiology, the threshold was more so close to the 10,000 data points scale. And finally, I think a consideration is economics of scale, right? So this is where, if you have a lot of users and a lot of requests, it can get very expensive very quickly to consume GPT-4 directly, especially if you need to include long context. So in the radiology example, each request for kind of chain of thought reasoning was on the order of 3 cents, right? So if you have millions of requests, this can really get out of control very quickly. So these are kind of the dimensions that you'd want to consider when determining whether you should pursue fine-tuning or not. So how does fine-tuning actually work, and how do we go about doing it, and what's available right now for you to start off with for fine-tuning? I think this really gets at maybe some limitations of consuming APIs directly from, say, OpenAI or Anthropic. It really limits the kind of the algorithmic approaches that you can take when it comes to fine-tuning, right? So even though OpenAI has a fine-tuning API, you only can control it by providing the data. You can't determine how that fine tuning is performed. But if you go the route of open source models and owning your own language model, that the possibilities of how you do that fine tuning expands tremendously, right? So, and it allows you to go from proprietary data and fine tuning an open source model so that you get a proprietary model that can give you much more customized outputs. And we've seen a lot of very powerful models kind of emerge in the open source. And there's one line missing here, which is Llama 2, 70, which the largest model, which is 70 billion, which is actually licensed for commercial use. And it's been shown to be competitive with ChatGPT. So more and more we see that fine tuning an open source model is a very viable approach to customizing models for your own data. So how does fine tuning work? There are quite a few different flavors of fine tuning. I think traditionally we saw like what's called like frozen pre-trained fine tuning, where the feature extractor is frozen and only the prediction layers at the top or in this case at the bottom are updated. And this worked pretty well for vision tasks, but for language models, we've seen full-time fine tuning where all the layers of a model are updated with gradients in a backward pass perform much better than the frozen fine tuning that used to be much more common. So why is it so hard to fine tune these language models? And it really gets at the massive size of the strongest or of the most high performing models these days. So in this table, I'm showing the rough GPU memory requirements of different sizes of models. And so you can see for, let's say, a 20 billion parameter language model, you need basically 2x the size of the model for the weights and the gradients, and then almost like 12x for the atom optimizer, right? So there's some very large multipliers over here for that's needed for training. So in particular, the optimizer can take up a lot of GPU memory. So for a 20 billion parameter model, in total, we're looking at 320 gigabytes of GPU memory requirement, which obviously does not fit on even the largest GPUs that we have these days, which means we have to turn to other approaches to spread the model across multiple GPUs. There are different approaches to do that along the lines of model parallelism or optimizer state sharding that can help you tackle these much larger models. So there's specialized techniques that's needed, and oftentimes you have to optimize these additional hyperparameters in order to get the best throughput and avoid out of memory errors. So it can be quite challenging to do full fine tuning of these models at scale. We've seen more parameter efficient approaches being developed, and probably the most popular of which is called LoRa. And this chart kind of shows you the performance of different parameter efficient fine tuning techniques as a function of the percent of parameters that they update. And we see basically a rough correlation that the more parameters you update, the better. The results of PFT versus full fine tuning can be pretty mixed. So oftentimes full fine tuning still does better, as you see kind of in the bottom table. But parameter efficient techniques provide us a way to fine tune these large language models without requiring nearly as much GPU memory requirements. So what this means for you is, I think there's a lot of opportunity for language model applications in different industries to really customize the open source language model on custom data. And we make that very easy to do with our open source deep learning platform called Determined AI. And here I'm showing a learning curve where for fine-tuning Vicuna, a 7 billion Vicuna based Llama 2 based model with LoRa. And we make it very easy to track your experiments and store your checkpoints and come back to your experiments to analyze them later so you don't lose work. If you've ever had projects that balloon to hundreds of experiments, I think Determine could be a really useful project or useful library for you. So check it out. It's very easy to do these days with the Hugging Face libraries. And we also have integrations with Hugging Face, et cetera, to make it very easy to do on Determine. So, a lot of the many times I get questions about kind of when to use fine tuning versus prompting. Covered a little bit of the desiderata in a previous slide, but here's a useful decision tree if you find yourself asking the same question. And that really brings me to kind of the second case study for information retrieval. I think one decision point that might not come up as much is whether the task you're trying to solve requires guarantee of factuality or needs access to frequently updated information, in which case a lot of the typical ways of using LLMs need to be augmented with some sort of knowledge base. And this is kind of what's emerging as a paradigm called retrieval augmented generation, or in this case, an information retrieval LLM powered information retrieval application. So how does this system work, and why would you care about the system? I think one really appealing thing about information retrieval is how it improves LLM hallucinations or reduces the occurrence of hallucinations. And we see hallucinations happen quite frequently. So, as an example, if I ask GPT-4, like, where is the McDonald's at the Seattle SeaTac airport? It actually responds with the wrong gate, right? So it says near gate C2, even though the McDonald's is actually at the B gates, right? So why does this happen? I think to reason about it, it's very helpful to go back again to the probabilistic nature of language models. And, if you think about the probability distribution associated with predicting this sequence, what's happening is that the gate C2 has just much higher probability of occurrence than the B gates. And that's probably associated with the training data. And maybe there are more McDonald's at gate C2s than there are at B gates. So how can we prevent this sort of behavior when we really care about extracting factual information? And that's kind of where information retrieval or RAG type applications come in. I want to motivate it with a case study in finance. And here, let's say we want to build a chatbot to answer questions very specific to banking. Right. So the data that we have access to are sort of question, passage, answer tuples. Right. And there are kind of two approaches to building such a chatbot. One approach kind of uses all the fine tuning tools that we covered before, where we can just use the question and answer pairs and fine tune a language model on the question and answer pairs so that when a new question comes in, hopefully the language model will be able to answer it. The second approach via information retrieval is to actually have a separate model that's kind of in charge of retrieving relevant passages and giving that along with passing the question along with the relevant passages to a language model for the language model to synthesize and answer. So that's what I'm going to talk about next and how we build this sort of system. I also want to maybe just pause for a bit and compare and contrast the two approaches, right? So in the first approach, we just give a question like this directly to the language model. So what's the idea behind using gaming simulation techniques and scenario planning to tackle economic crime more effectively? And one way is to just take the language model and use it directly. And another is to retrieve the related documents that you see on the right and then have that language model synthesize and answer. And there are really two core components to an information retrieval application. There's a vector search component that's in charge of identifying the relevant passages for a particular query. And then there's a chat component that is in charge of understanding the user intent and synthesizing a response, giving the retrieved passages. So the vector search, how does it work? I think many of you are pretty familiar with this. I'll just cover it really quickly. Basically, you embed all the documents that you have and basically get vector representations of them, put them into a vector store. And when a new query comes in, you get the vector representation of the query and use the search mechanism in the vector store to return the most similar passages. Usually that's quantified with a metric like cosine similarity. And as part of a full information application system, this is kind of what that workflow looks like, where the chat history and the question come into the chat model, which can synthesize a context-aware question that gets passed to the embedding model. And then the chat model is finally in charge of taking in the retrieved passages and generating the answer. So, one way of customizing this sort of information retrieval application for your own data and going beyond just a standard API is to improve the retrieval component with fine-tuned embeddings. And if we think about why it could make sense to do that, here we're basically visualizing visualizing embeddings of different types of articles. And if we zoom in on business and finance, a lot of those articles just look like they are grouped into one big cluster. And if with retrieval fine tuning, we can learn embeddings that are much better at separating different types of financial articles. And in fact, in this in a customer POC that we did for banking, we saw this exact behavior where if we looked at ADA embeddings, we saw top one accuracy of 80%. If we took an off-the-shelf embedding like SGPT, which is a 6 billion parameter embedding model, we observed slightly lower retrieval accuracy. But with a fine-tuned model, we actually were able to outperform the OpenAI ADA embedding. So there's definitely a lot of value to be had by customizing embeddings as part of an information retrieval application. So this all comes together with our sort of workflow orchestration product called MLDM, and the open source version of that is called Pachyderm, and can combine that with Determined to build out a deployment pipeline for such an application that's connected to your databases, that can incrementally update the vector database when new data comes in, and it's all tied to a front end that we've built for the POC, but you can imagine this sort of same workflow for arbitrary information retrieval applications. So to summarize, I think there are a lot of benefits of information retrieval. It reduces hallucination by introducing facts into the context retrieved by like an embedding model. It provides audibility, so you can see what information a model used to provide an answer. It also is a way for us to bypass the context length limitations, because we can kind of chunk the document up into smaller pieces and basically retrieve just smaller chunks instead of looking at a whole document. And finally, it gives us a way to update the knowledge base separately from the model so that we can update the information that a language model has access to when providing a question at a much faster cadence than you need to update the model itself. So here's a decision tree for how you go about deciding whether to fine tune or not, mainly as a reference. And in conclusion, I think today, hopefully, given a few ideas for how you can go beyond just proprietary APIs and derive more value from language models for your own custom industry use cases, right? So I think the main decision point is probably how important it is to maintain control, keep your data private. There are also considerations around alignment trade-offs. You might care about fairness and bias more, or you might care about calibration more, in which case you can make those alignment trade-offs yourself instead of relying on the default alignment trade-offs provided by, say, the OpenAI APIs. Also gives you a lot more control over how and when a model changes. So there are many instances of OpenAI updating their models and breaking applications that depended on specific prompts that no longer worked with the new model, right? So if you maintain control over the models, you have a lot more control over breaking changes. And finally, if you are working with an open source model, it gives you a lot of flexibility in the types of approaches that you can use, especially on the fine tuning front. We also talked about how fine tuning in particular can help improve performance significantly by making use of all of your available data. And most of the time that the fine tuned model can be much smaller so that you can save on inference cost and also have faster inference speed. So some food for thought for various reasons and value that you might derive by pursuing your own language models based off of open source models like Llama V2 instead of consuming open APIs directly. So I will stop there. Thank you all for your attention, and feel free to email me if you have any questions.